Scientists is an initiative that's brought to you by a team at the University of California, Santa Cruz. I work for UC Santa Cruz, but I'm grateful to say that I have lived here. I saw that. Did you go to UC Santa Cruz?
Shout out UCSC.
Banana slugs. You know, that's just hard to say with any kind of emotion and not laugh. Yes, banana slugs. I'm grateful to be able to work remotely from this beautiful island. Now, an introduction to Gemini Observatory. So, in this session, we have the privilege of shadowing members of the Gemini Observatory North team. Now, the International Gemini Observatory consists of twin 8.1 meter optical infrared telescopes located on two of the best observing sites on the planet. Gemini North, right behind you, is located on Hawaii's Maunakea and is part of an international community of observatories. By incorporating technologies such as laser guide star, adaptive optics, and multi-optic spectroscopy, astronomers in the Gemini Partnership explore the universe in unprecedented depth and detail. Now, tonight's observations will be taking place in the Hilo Base Facility Control Room. So, let's go over there now. All right, Brian.
Aloha, Jameeka. You can hear me okay?
Yes, yes.
I'll take it by Eris screaming in the background that you guys can hear me.
Yes, yes.
Wonderful. Okay. Well, aloha, everybody. I'm Brian Lemaux. I'm a staff scientist here at Gemini North Observatory. And
Brian, hold on just a second. Let us see if we can make your volume higher.
I'm not sure if you can adjust his mic at all. So that this might be the highest that everything goes from here.
This bad?
Yes.
Sound better?
Can you talk more directly into your microphone for us?
Can you hear me okay?
Yeah, we can hear you. It's just a little low. Yes, yes. And your wonderful son is seeing you and is congratulating you already for a job well done. Yes, give it up for Erin. Yes.
You guys hear me better now?
All right, so.
Does that work, Jameeka?
Oh, that is better. Yes, Brian.
Much better? Okay. Okay.
It is.
Okay, aloha, everybody. I'm Brian Lemaux. I'm a staff scientist at Gemini North Observatory. I am at the Hilo base facility. I'm so excited to join here tonight in Hilo. We've never done this before. We've never broadcast downtown. We're trying lots of new things tonight, so bear with us if we're having some technical difficulties. I'm just going to share a few slides to get us oriented about the observatory. Okay, y'all can see this?
Yes.
Yes, okay, good.
Yeah.
Okay, so y'all already know, re-anniversary edition, 1 year. Super exciting. We're super honored as Shadow the Scientists to be here tonight. Just a quick overview. I know Emily introduced me already, but I'm a staff scientist here working for 3.5 years at Gemini North. I have been coming to Hawaii and to Mauna Kea for observing for more than half my life, 22 years. As was mentioned in the beginning, my research is in finding the biggest structures in the universe. So I need really big telescopes to look really, really far away to try to find structures of galaxies that contain tens, hundreds, thousands of galaxies, all in the same distance as the distance between, for example, the Milky Way and the Andromeda Galaxy, which is our next major companion galaxy here. I'm originally from California. I moved here with my wife, Deborah, who's in the background there somewhere in Hilo Town Tavern. And our little guy is Eris, born in Hilo, and he's probably screaming right now. And so this is what I look for. This is just a really quick overview of the types of things that I look for. These are structures, these are density maps of galaxies that myself and collaborators made. And this comes from, honestly, tens or hundreds of hours on large telescopes like Gemini, Keck, Subaru, and telescopes in space like James Webb and the Hubble Space Telescopes. This is just a representation. This particular structure is we discovered when the universe is about 2 billion years old, so about 15% of its current age. And this is just kind of an artist rendition. It is actually the density map, but there's hundreds of galaxies here that are all about the same mass as the Milky Way, all clumped together. And so they're all interacting. They're inducing star formation with one another. They're turning on each other's black holes. So all sorts of wonderful activity, and it's super fun to study this kind of stuff. So there's no serious plan here. Y'all are welcome to raise your hand any point, shout out. I can't really hear like super awesome, but I'm sure Jameeka can relay questions. We'll just do a quick.
No worries, I got you.
Okay. So quick overview of the observatory and its capabilities, and then we're going to check in with the night crew, and then we'll see what's going on. So these are the 2 telescopes of the Gemini International Observatory, 8.1 meters in diameter. So what is that, 27 feet, something like that. So quite large. That's just the aperture of the primary mirror. So the amount of glass that's there that's reflecting the light from the distant universe or from the solar system or whatever we happen to look at. It's infrared optimized, so for light that's redder than we can see as humans, but it also covers the optical part of the spectrum as well. And we do imaging, so we basically take a lot of astronomy is basically taking pictures or breaking up the light into its constituent parts, so into a rainbow, and then analyzing those data. And we have 6 partner countries: United States, Canada, Chile, Brazil, Argentina, Korea, and then the University of Hawaii here. So as I mentioned, optical and near-infrared capabilities. On any given night, we have a full queue of observations that are submitted by scientists all over the world. And we use so we use the telescope to collect the light, but we use different instruments to then kind of transform that light in some way to be scientifically useful for different purposes. So this is a lot of text, but the main instruments that we're going to be using tonight is GMOS North, and in fact, I think we're using that right now. So this is a imager and also a low resolution a spectrograph or medium resolution spectrograph. And so I think actually the night crew is taking a spectrum right now, so I'll try to go over there before too long. And then GNIRS, my favorite. Everybody loves GNIRS. That's the Gemini Near Infrared Spectrograph. This is a Swiss Army knife instrument. It basically does everything. It does spectroscopy. It does something called integral field unit capabilities. GMOS North also has that. So it basically takes a rainbow of every single part of the sky that it's looking at, and you kind of stitch that together and get a lot of information about the chemical abundances, for example, or the movements of astronomical objects. And it also does imaging. So I think Maroon X was mentioned earlier. I think Emily said something about it. So Maroon X is, we just got it back today, actually. We had an issue and we had somebody fly out from Arizona. We found out about the issue on Tuesday, I think, and they flew out from Arizona, arrived here, went up to the summit of Mauna Kea today, and fixed the issue. And so we're observing with it tonight. So this is just to speak to how like the amazing teamwork that happens at the observatory and how it's truly worldwide. And so as I say here, Mauna Kea has two of the best space rainbow makers on the planet. Maroon X is one of them. The other one is Keck Planet Finder on the Keck. I could forget if it's Keck 1 or Keck 2. But it's basically these instruments. So you have the telescope to collect the light, and then it disperses it into really tiny quanta containing basically 80,000 different colors in the optical spectrum. And so you get really, really fine gradations, differentiation between red and a different type of red. And what you can measure from this is exactly what's shown on this video here. This is the one of the things it can do to look at the movement of a host star in another solar system as a planet goes around that star. So you see the shifting of these black lines. So you see the rainbow, and then you see the shifting of the black lines as the system moves around. And so this is how extrasolar planets, at least one way that extrasolar planets planets outside of our solar system are found. And so MaroonX is one of the most sensitive instruments on the entire planet for doing this. And we have the privilege tonight of taking a look at it. Gemini South, so we're twins, but not really. This is in Cerro in Chile. So we can actually see the whole entire sky at once. They're 7 hours, about 7 hours offset from us right now. So they're in the truly in the middle of their night. But they have a similar sets of capabilities, but they also have complementary capabilities, and I won't go into the details here. So y'all ready to get to some observing?
Yeah. Yes.
Let's do it.
Now, Brian,
So I'm going to stop share, and I might just go to the control room. So if it's not too busy in there, if people can introduce themselves, night crew can introduce themselves.
I have the control room pinned, so you and the control room are pinned, and we can see people. Yes. Hello.
Hey guys.
Yes. Yes, Matias, Jen, and Eunchong. All right. Aloha. Yes, please give us an introduction. Let's start with you, Jen.
Hello, my name's Jen Miller. I'm a science operations specialist here at Gemini. We actually are just starting to set up on a new target, so we're a little bit busy at the moment, but we have like a few minutes to talk. We can also come back and talk more once we're set up.
Yeah, totally. I can why don't I show what you guys just took, and then we can come back to you guys.
Okay. Yeah, it's a flat was the last image, so it might not be very exciting.
I see it, at least I see on SegPlot that you have the IDL SegPlot, you have a spectrum, so that could work. Awesome. Okay, so let me share. So so just to give you guys an idea, so Jen and Eunchong are observers tonight. So we have two different roles. This is different from every single observatory, but at Gemini we have what's called the observer, and the observer is kind of the person with the scientific roadmap for the evening. So as I mentioned earlier, we have anybody in the world is allowed to apply for Gemini. It's one of the only big telescopes where that's true. And so you submit your idea as a scientist or as an amateur, and you say, hey, I think this is a really good idea. A team of scientists that are kind of randomly selected from all over the world, they analyze your proposal, and they do it anonymously or dual anonymously. So you don't know who they are, they don't know who you are. And they say, this has merit, this doesn't have merit, or this is a really good idea, but we don't have enough time on the telescope. About 10% of people that apply get time. So it's very, very competitive, and that's normal for large telescopes. So you have to have a really good idea, or you at least have to tell a really good story. And so Eunchong and Jen are they have the different plans available. So there's a suite of observations from all these programs that were selected, and they're assessing the weather conditions, what the demand is scientifically for each individual program. So you can imagine, just to ground it, you can imagine if you're looking at something really bright, like let's say you're looking at the Andromeda galaxy, and you just, you want to see the brighter stars in Andromeda that's quite close by, on cosmological terms, let's say, still 500,000 light years away. Maybe you can deal with a little bit of clouds. So on a night like tonight, where it's a little bit cloudy for Mauna Kea, this happens about half the time of the year, that you can look at brighter targets. And so if Eunchong and Jen saw, oh yeah, there's clouds rolling in, and we can take a look at what's going on up at the summit now.
Yeah. Can we look at some of the weather cams, Brian?
Yeah, absolutely. So this is available to everybody. This is our Gemini North status page, and it has all sorts of really cool information. But this is our super light sensitive cameras. So this is what the observers are using right now to be able to tell what the conditions are. And so this is pointing east towards Hilo. You can see, hey, it's not cloudy in Hilo. Surprise. And then south cam, west cam, north cloud cam, and then our up camera. And so you can see there's wispy clouds running in, and this is a radar right here. So you can see there's a ridge just to the northwest. And so there's clouds there. And so we might choose a program that had a little bit brighter astronomical objects associated with it. If there's no clouds and the turbulence on the ground and in the air, the atmosphere is pretty low, then we would really go for deep things in the distant universe. And so Jen and Eunchong have that map. And because we're doing this remote observing, so our telescope has nobody up at the summit right now at nighttime. So there's people that go up during the day, but right now there's nobody. And so we have to have all this information, all these different sensors, and actually the observatories work together. So you can see over here, this is from James Clerk Maxwell telescope and the submillimeter array. This is the amount of water vapor above Mauna Kea in the atmosphere. This is from the Canada, France, Hawaii telescope. This is their measurement of the attenuation in the atmosphere. So basically how many clouds there are. We have a turbulence measure from Canada, France, Hawaii telescope. We share our information. And so also, as many of you probably know, Kilauea is going off right now. And so we have particulate sensors that help us. This can be very damaging for the telescopes. And in fact, the group last night had to actually the entire summit had to shut down for about an hour just because people were smelling sulfur dioxide up at the summit. So the observatories truly work together to make sure everybody's safe, sound, and we all get our the science that we can that's possible. So I will share now this screen.
And we're at 9 minutes left for this segment, Brian. 9 minutes.
Okay, sounds good. So this is just one of the million screens that that we have at our disposal on a given night, and you can see there's just tons of information. And so the observer has to be really careful. So I'm sharing Eunchong and Jen's screen right now. This is a live screen. I forgot to mention that Matias is also there, Matias Rodriguez, and he is our operator for tonight. So he's actually slewing the telescope, so moving the telescope with different so he moves our different optical elements in the telescope. He actually slews the dome, so move the dome, move the telescope. So Jen and Eunchong work in tandem with Mati to get to the place in the sky that we need to be, and then directing the light in the right location for the scientific program. And so this is the observation that Jen and Eunchong just took, and Mati drove us there. And this is a spectrum taken from GMOS. So you can see in the background here, this is, so basically every observation that we take is black and white. And then you can assign like false colors to it. There truly are colors associated with it, but we have to do mathematical modeling to try to figure out what is actually red and blue. You can see, maybe, probably not, but here we have this helpful display that says red this way, blue this way. It's almost like Alice in Wonderland-ish. And so this is because it's displayed in black and white. And it's truly assigning like a wavelength number to each location on this detector that we need to have that orientation. And so this was what's called a standard star. We take an observation on a given night, and of course there's conditions, there's clouds, there's turbulence. Our telescope has optics associated with it, so there's reflectivity. It's incredibly good at reflectivity, but it's not perfect. And so we have to take out all those terrestrial effects and get to the intrinsic nature of any source that we observe. And so that's what we take. We take calibrations at the beginning of the night. This is very normal. And that's what Jen and Eunchong just took. So probably, let's see. So Jen and Eunchong, are you guys free to talk about what y'all are doing right now?
And Eunchong is checking the slit position. We're setting up on a new target.
Okay.
You can see that actually in the other sec plot, the image that we just took, if you want. It's not very interesting. It's just we're just putting the object in the slit.
Yeah, so this one here, y'all can see my cursor. This is the target probably in this colored screen. This is the target, and so Eunchong is centering. So we do like the coarse movement of the telescope, and then we do these very fine movements of the telescope to make sure that we get the light exactly where we want it. And this is important because we have the privilege of observing from Mauna Kea. We want to take every single photon that we possibly can out of this observation, because a lot of these things are extremely faint, and even with this enormous telescope and these wonderfully sensitive instruments, you want to make sure that you're really where you think you are.
So real quick, first, any questions? We have Brian and the team in the control room for another 5 minutes or so before the break. Questions, please shout them out, or you can come on up. Anyone? Comments, we'll take comments too. So feel free to just let me know. I'll pass them along. Yes.
Great question. So the question was, have you looked at methane on Mars, in the atmosphere of Mars? Is that a capability that Gemini has?
Methane emission, so yes, in principle. I personally have not. In principle, methane emission could be detected in the near infrared. So the Gemini near infrared spectrograph, if it were pointed at Mars, and if you set the exposure time to be really low, because Mars is quite bright for Gemini, you could probably do it. I know that several staff members here work on the atmosphere of Neptune and Titan, the major moon of Saturn. So these are observations that we certainly take. I think I've actually been on nights with Matias where we've observed Titan, and that's really spectacular. So yeah, that's totally possible. We do stay in the solar system every once in a while, and yeah, we track asteroids, we track comets, and we measure planetary atmospheres. So that's pretty normal for us.
Excellent. Excellent. Thank you for that question. Other questions? Other questions?
How long does it take to do an observation, and about how many observations on a clear night are they able to do?
Great questions. Okay, so first question, how long does it take to do an observation? And the follow-up is, how many observations can you do in an evening?
Yeah, so that's a great question. It varies tremendously. So we have an instrument called Alopeke, which is a Hawaiian word for fox, and it is what's called a speckle imager. And what it does is it basically just kind of disperses the light of a star, and it takes really rapid images, like on the kind of millisecond or microsecond level. So tons of images, and it does it. It's looking at bright stars. So it's about five minutes per observation, and the staff are not happy when they're scheduled on Alopeke nights, because you are looking at like 100 targets per night. So it's just move. Now, the things that I look at, probably the staff are pretty happy, because the observations that I generally take are sit on something for 8 hours, just stare at it, and maybe you get like 10 photons, and then you're happy and you say, okay, now I can do some science with that. So it really, there's observations that you would sit on something all night long, single or maybe 2 observations per night, and there can be like 100 observations. And so it really depends on the science, the type of object that you're looking at, the instrument that you're using, the telescope that you're using. For example, the near infrared. So if we're observing a near infrared, that can be much more difficult. It is much more difficult on the ground because the atmosphere is very bright. But if you go into space and use an instrument like a telescope like James Webb Space Telescope, those observations can be much shorter. But then Gemini has other advantages. So it really depends on a variety of different conditions.
Thank you. Great questions. Other questions? Yes.
What is the temporal dynamic range of this telescope?
What is the temporal dynamic range of this telescope?
I think I need more clarification. In which way?
How close in time can you look, and how far back in time?
I see what you're getting at. Okay, so right, so we can observe things that are very close in the solar system, so light minutes, effectively. So the light that we're looking at for solar system objects was emitted, if it's close by, let's say as close as the sun, is something like 8 light minutes away. And then we also look at the very edge of the observable universe. So the dynamic range is total as far as humans see it. And so we look at galaxies that are about 500 million years after the Big Bang. So when the universe was roughly 4% of its current age, the first galaxies that formed in the universe.
Wow, we got some wows. Excellent. Thank you.
What's the most exciting and memorable thing you've ever seen?
Did you get that? What's the most exciting and or memorable object you've ever seen? Ooh, that's a hard one.
Oh gosh. I don't know. There's so many to choose from. I like honestly seeing the stuff that I look at, it's just little red dots. And it's so exciting for me when I get a spectrum. So you see a spectrum on your screen right now. When I see a spectrum, the types of objects that I look at, you wouldn't see any of that trace there. So that trace is just basically the rainbow of the source. What you would look for is just one little tiny dot in this forest of atmospheric lines. You're searching through the noise, and then it just pops up, and that tells you. So the emission tells you how far away a galaxy is, among many other things. And so you're targeting something, and you're looking, and you're like, I wonder how far away that is, and I wonder what the properties of that source are. Is it close by, or is it really, really far away? And there's degeneracies when you're trying to understand just from an image if that's true or not. And so you spend 8 hours on a telescope, and you try to squeeze every single photon that you possibly can out of that observation, and then you get it back, and it looks like this, right? It's just a bunch of this is like atmospheric lines, and you're like, man, I didn't see anything. But once you spend all the time to reduce it, and we don't have time to go into that process, but basically remove the terrestrial effects, so on and so forth. And a little tiny signal pops out of that, and you say, oh my gosh, that galaxy is 12 billion light years distant. Come on. If you're not excited about that, then you're in the wrong job. But Titan is also cool. The solar system is also cool. Watching things move on a human time scale in space is absolutely cool. We can do that with asteroids and comets, so that's very neat. I think we're about out of time. I just want to give a chance to the control room if there was any last things to say.
Yes, because the spectrum down here has, can you
I'll share back
that again real quick? Yes, thank you so much. The spectrum has changed, and I see, there are some things going on with GMOS. GMOS is acquiring, and I don't think we said what that is. That's the Gemini multi-object spectrograph, and is reading out. So the spectrum has changed. What's different here, Brian?
Well, I'll pass it into Jen and Eunchong if they're not too busy to explain what they're looking at right now.
Jen and Eunchong.
What was the question?
Oh, just what we're looking at right now, and the fact that the display changed. So I saw there was a science spectrum, and then it looked like an arc spectrum and a flat spectrum.
Yeah, so we're running through a sequence. So we take the science, and then the science also has some calibration data. Do you want to?
Yeah, we are taking data.
Can you speak just a little bit into wherever the speaker is?
Sorry, what was the question? Sorry, I couldn't hear.
What are you looking at?
Oh, this
Yes,
program
thank you.
wants to see the agent activity. This means a supermassive black hole in the galaxy.
Brian,
Right.
can you repeat that for us?
Yeah. So what Eunchong said is that so right now we're taking spectra, so we're basically dispersing the light out with this GMOS spectrograph, and this is a science spectrum. So what you're seeing right now on the screen, this colored portion, this is the rainbow of this object. And what Eunchong said is this particular program, so that we have lots of different programs, this particular program is actually looking at the emission of a black hole in the distant universe. And so this is emission around a black hole. This is what's called an accretion disk emission. So as a gas and dust and planets and humans as things fall into the black hole, you get this accretion, everything heats up, and so it emits, and this is the emission from that black hole. So black holes themselves don't actually emit light by their name, but you see this accretion disk around, and this is what we're taking the spectrum of. And so they get some idea of the properties. You can actually measure the rotation of that black hole. You can measure the energetics. And so what Jen was saying is that we're taking calibrations because we're trying to remove that terrestrial effect. So we want to get to the intrinsic, what's intrinsically happening with that black hole. We got to remove all our optics and our atmosphere and all this kind of stuff. So that's what we're doing. So I think we've reached the kind of the limit here. So I
Yes.
will see you guys after the break. Yeah.
Yes, we'll come back and check in with you all just after the break. Thank you, Brian, Jen, Eunchong, Matias. You've been amazing. Haven't they been amazing? Yes. Seeing all this data coming in real time is absolutely fantastic. Okay, so now I'm going to hand it back over to Emily for break time.
Okay. Thanks, everybody.
All right, so that is, we're gonna be back with the Shadow the Scientist team in just a little bit, and we're gonna take some time and we'll do some fun things. We'll start with having maybe about a 3 to 5 minute break for restrooms, refilling your drinks. However, I just wanna kind of talk about, I thought I adjusted the slide, but I don't think I got that. A few of our different programs that we have as Maunakea observatories and as Gemini observatories. You guys might have read in the news that the Hawai'i observatory experience has restarted. March was our first Hawai'i observatory experience that was fully open to the public. We have another one coming up on this Saturday that is completely full. We are so happy. We're so happy. We're all excited. I know that we have a lot of regulars here at Astronomy that was some of our first public in order to sign up for the Hawai'i observatory experience. I'm going to say, as soon as it got released in the newspapers, our wait list went from 0 to 300. So it's going to take a while. But keep in mind that the Hawai'i observatory experience, the sign-ups and the reservation for Hawai'i observatory experience is always going to open a month before the next tour. The normal time for Hawai'i observatory experience is it will be the first Saturday of the month. However, we are skipping the month of May because the first Saturday of the month of May is Astro Day. Woo! Experience are going to be taken up at Astro Day. So if you still want to talk to some observatory folks, please join us at the Hilo Mall for Astro Day, where we're going to have different booths for all the different Maunakea observatories as well as different science organizations set up throughout the day on Saturday, May 3rd. And of course, in the center here, we also see the Shadow Scientist at Gemini North Telescope. If you are intrigued by some of the things you're learning about and you want to be seen and participating in more Shadow the Scientist sessions, Shadow the Scientist is a completely free program. You follow this QR code to all of the upcoming events in April and new ones added all the time, and not just in the Shawnee, but with many different programs across the world of our different events. One thing I also meant to put in here, but doesn't seem to put in, is in addition to our Hawai'i observatory experience, our Shadow Scientist, and Astro Day, we do offer tours of Gemini North Telescope and of the Gemini Hilo base facility. These are all free and open to the public and include some links for you to be joining in on those as well. Okay. And goodie bags. No, never mind. Okay. So, but now, as I mentioned before, this is the first anniversary of Astro on Tap here at Hilo Tavern. We want to thank you all for joining us tonight. Even though it's our birthday, you're going to get presents. So our wonderful Astro on Tap team is going to be coming around to the different tables with our fantastic packages and presents. Yes, we'll do a quiz in about 5 minutes. We don't quite have music tonight because we're connecting to our music speaker with our Zoom. If you guys really want to, I can sing. You don't actually want that. Yes. The Astro on Tap. I'm going to jump back to it. Let's go. We don't talk about this logo enough, and it's a really cool logo. For our Astro on Tap here in Hawaii at Hilo Town Tavern, Our logo is featuring astronomy on top at Hawai'i, with of course our Hawai'i Islands. Our recognition of being on top, we have a nice spear glass where the color is making a beautiful galaxy. And then incorporated with it, we have the Va'a of Okulea and the navigational star family of Hawai'i or the back. This is the star family that connects from the North Star to the Southern Cross and incorporates the star family. So you put in the star family, North of Maunakea is kind of back in the history. And all of these videos are considering a magnet that includes our astronomical. We'll have to try 5 minutes and then we will do our quiz. As a reminder, during our break, we also have our poll. All the ingredients to our poll go to our Astronaut prizes. So if you're thinking that you're going to win a really good prize in one of our Astronaut caps, our question is, do wormholes exist? During our break time, if you want to come up and discuss it with me, get yourself. All right, everybody, are you ready? Beginning our quiz moment. You're in the prepare yourself for the quiz. You scan our QR code. We do ask for honor system All right, everybody, we are going to get started on our quiz. Right off, I'm just going to QR code. It didn't have to be the time or the name right away, so let's lean on this seat for a little bit so we get people ready in order to enter in their names. The team players ready.
You can also read out this code. Here, this one.
You can also be joining in at menti.com. The code is
Maybe read it out small.
870758. All right, everybody, we will be starting the quiz in 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. We lost the player, but then came back. Okay, we got 21 players for our quiz. Let's get ready to rumble. Our first question. The fast answer is going to get more points. What is dome seeing and how can it affect observations at a telescope? It's when the dome aligns perfectly with the star. It's a phenomenon where the dome lights up due to moonlight. It's turbulence caused by temperature differences inside the dome. It's a visual effect seen when looking at the dome through binoculars. 15 seconds to answer. We have half of the crew. Who talked about dome seeing? Was that Peter Michaud talking to us about taking?
Last month.
Last month was when Peter Michaud was talking to us about dome seeing. All right, and the answer is turbulence caused by temperature differences inside of the dome. And we have 10 participants. It's a majority. Let's see what our ranking is like. Our crazy board. Drum roll. And Thomas. I look how Thomas, your icon is a train. That feels very on the nose. All right. Question 2 of 13. A typical solar flare is about the size of the moon, the Earth, or Jupiter. It's our favorite star, the one that provides us light. How big is it solar flares? Oh, okay, we have everybody in at 21. 10 seconds to go. Oh, sorry, we have 22 years. Everyone has voted. Oh, okay. And the answer is Jupiter! Yeah, okay. We're doing pretty well so far. Oh, look at me. That's actually just something I was like on the top of my head. I don't look at the sun, I look at galaxies. And who is coming up ahead? Oh, Johnny Tsunami. He's retired from surfing and is now competing in our competition. What color is an old star usually? Green, blue, yellow, or red? Do you guys know that stars have colors? Yeah. Yeah. What color is the star? It's really, and it looks old. 15 seconds. Okay. 3, 2, 1. And answer is red. 17 participants got it right. Oh. And Johnny Tsunami maintains the lead, and Mr. Ashton Roller Roller is in second place. I got it, Ashton. What in the atmosphere makes it difficult to look at the stars? H2O, water, CO2, carbon dioxide, or N2 nitrogen? What makes it hard to look at stars? I think this might be a little bit of context.
This was one of the hardest questions last year.
Really? Jameeka's telling me it's better knowledge. This is one of the hardest questions. I'm wondering if I'm overthinking it. Okay, 18. Water is the correct answer. Is that because of clouds?
No.
No? Okay. If it wasn't water, I would have argued it's water, because in Hilo, that's definitely our biggest challenge looking at the stars. Water. And Johnny Tsunami knows his water. And Johnny Tsunami maintains the ring. Thomas is coming back up. Question 5 of 13. What is the name of the star system Jedi Master Yoda lived and trained Padawan Luke Skywalker in? Dagobah, Kulivin, or Bakura?
This is from our May the 4th event.
Oh, funny story, for a long time I would write the star charts for the newspaper to be used as our advertiser, and for many years we kept misspelling Aldebaran, the star, as Alderon, and no one caught it. Until Star Wars came out. Okay, the Dagobah system. Okay. I think we have a lot of Star Wars members of our audience. Okay, our top three is not having a lot of different dreams. We got Johnny Tsunami, Mr. Astronomer. It's hard to say when I'm reading for some reason. And Thomas are our top three. That's question 216. Moon or frying pan? So take a look at the image on your phone. Is that image, which one is the moon or frying, left or right?
Which one is the solar system?
Oh, which one? Which left or right image is the moon of the solar system?
No, not the.
Oh, it's this is why it tripped so many people up last week. That was Saturn's moon in Celadus. It looks like the underside of your frying pan. Yeah, nice. You're not my moon. Hashtag not my moon. Oh, let's see what's happened. Oh, Mr. Astronomer is taken over from Johnny Tsunami. Sleeping Eris underscore A is coming up as well. I'm going to be Sleeping Eris. What would happen if you replaced the sun with a black hole of equal mass? As an educator, I get asked this question many times by kids, and my first answer is something bad. It would get really cold. All the planets would collapse into it. All the planets would float away. This is a black hole that has the exact same mass as the sun, which means its physical size would be much smaller than the current sun, but its gravitational influence would be the same. That's a great hint for you. Gravitational influence would be the same. And the answer is, it would get really cold. Yeah! Some will pull up. Yes. As the communists and stuff go, oh, little penguins. They're all ready. Okay, let's see who we got coming up. Ooh, Thomas is coming up. And Thomas the Train Engine is right on up the score. What if the solar system was the size of a grain of rice? We asked some philosophical questions here at Armstrong. Oh. If the solar system was the size of a grain of rice, how big would the Milky Way galaxy be? The equivalent of Hawai'i, a watermelon, or an atom? Rice. A grain of rice. So the solar system, so the sun, the 8 planets, asteroid belts, everything that impacts our solar system, not the size of rice, is the Milky Way galaxy now the size of a watermelon, Hawai'i, or an atom? There you go. It would be about the size of Hawai'i. And atom is much smaller than the Earth. Oh, okay. Let's see what's going on with our scoreboard. Oh, I thought Thomas was about to take over Mr. Astronomer there. Yeah. Okay, question 9 of 13. As a reminder, these are all our tricky questions. What is the Hawaiian name for the new moon phase? Hilo, Muku, Maui. I know, yeah. Or we get some of your wonderful tools that you can get out basically books like that. And the answer is Muku. For those of you who got tripped up by Hilo, Hilo is the phase immediately after the new moon phase. That's your
I already texted people that were
like
sending
the
this
very
Yeah, okay, good. Excellent. I put it in the chat too.
Muku is the new moon phase. Oh, there's no moon in the sky. Okay. Ooh, Johnny Tsunami might be having a comeback. Let's see here. Oh, Johnny Tsunami comes up in second place.
1 point.
Mr. Astronomer is taking the lead. Is this picture the sun, Jupiter, or Sallum? I have my reaction on top. So I don't even know.
Sun, Jupiter, or the delicious Saturn? That's a lot. That's a lot. That's a lot to keep up. It is Jupiter. I had a feeling for Jupiter. I was in Jupiter infrared. You know, looking at the heat energy. I had 7 people who guessed correctly. Oh, we're getting some back. Coming up with that race. Okay, Johnny Tsunami takes over, Mr. Astronomer. How big was the asteroid that killed the dinosaurs 66 million years ago? And how big was the crater that it created? 2 miles, the crater size of Molokai. 2 miles, crater size of Maunakea. 6 miles, crater size of Hawai'i Island. 6 miles, crater size of Hawaii. So you guys check out the dinosaur exhibit.
Yeah, don't worry. We run it 5 to 10 minutes. Yeah, I'm glad we built some
I wonder if we're gonna have the dinosaurs right there.
Yeah,
Oh, 6 miles, and the crater is the size of Hawai'i Island. So people got it right. Oh. All right, Mr. Astronomer, he takes the lead. I think this is going to be another picture question. Oh, it's not. Okay. Why is dark matter called dark? Because light cannot escape it. It does not emit light. We do not understand it or its color. Why is dark matter called dark? And it does not emit light. That's something to do. I'll also argue a little bit you don't understand. Yeah. That's it.
it's not the reason.
It's not the completely wrong answer. It's not the most correct answer. Okay, that didn't shake us too much. Matt, the cheeseburger is rising up tonight, so we'll see if we get a ticket from Matt, the cheeseburger. There. Oh, final question. Drum roll. What is the difference between a meteor and a meteorite?
Oh, yeah.
A meteor orbits the sun, while a meteorite orbits the earth. A meteor is a rock in space. A meteorite is a rock in our atmosphere. A meteor burns up in our atmosphere. A meteorite reaches the ground.
These are really good.
Yeah.
People got it right.
Yeah.
Okay. Let's get that drum roll for an hour. Okay, our theme is Mr. Astronomer. Mr. Astronomer. Our prizes are Hawai'i Rising, a wonderful book recording the history of modern navigation and the Renaissance of modern navigation. I think Mr. Astronomer is coming right up.
And we had.
All right. Excellent. And then, in honor of our anniversary, our 2nd and 3rd grade prizes are shot glasses.
All right. Woo! All right.
The Gemini shot glass or the Keck shot glass.
Yeah, that's the right choice.
And our first prize of our WM Keck shot glass goes to Thomas, who wrote the check and then all the way up.
Oh. Oh
They collaborate on this. I know. Okay, it's over to you again.
All right. We're gonna pass it on back to Jameeka for a continuation of Shadow the Scientist. All right, okay, all right. Let's give our amazing MCs a round of applause. Yes, and what about those prizes? Yeah. Excellent, excellent. Okay, so we're back into our Shadow the Scientist session, and we are going to check in with the control room. Let me see what's happening here. Let's remove this spotlight. All right, yes. Okay, all right, we were gonna check back in with Brian Lemaux, right? This was, our science host with Jen and Eunchong and Matias in the Hilo base facility control room, but their camera seems to be off, so I'm not sure where Brian is. Brian, can you hear us? Okay, so Brian is actually here. Let's give him a round of applause. Welcome. Thank you. Yes, welcome to the stage in person. All right, come on up. Welcome, Brian.
Bye.
That one's yours.
Okay. Hey everybody! Aloha! So what do you think if we go to a different telescope maybe?
A different telescope, can we do that?
I think we can do that, yeah. As we said, we're a wonderful community, all looking at the stars together, and it looks like we have somebody connected there.
That's right, I think we do. Who is that? Is that Viraja, Lisa, Benoit? Yes, we have the Canada, France, Hawaii Telescope Control Room on the line with us. Welcome.
Thank you so much, Jameeka. Can you hear me?
Okay, so you're now co-host, Benoit. Let me take care of you as well. And there's that, and your other screen also, Viraja, just a moment. And there we are. Okay, so you should be able to unmute yourselves and say hello. Can you hear us?
I can hear you. Can you hear us?
Yes, we can hear you. Yes, we're getting a round of applause here. Yes. Could you speak a little closer to your speaker?
Okay, sure. Is that good?
Yeah, yes.
Okay, all right. So hello everyone. I am Viraja Khatu. I am a resident astronomer here at the Canada, France, Hawaii Telescope. And we have 3 other people over here with us today. So from the Waimea control room over here, we have Lisa, who is our remote observer. She is going to be very busy right now, so but she'll jump in whenever we need her. We also have Roman here in the control room. He's a student, a master's student from France, who is working with Benoit on CETEL data. So it's exciting to have him in the control room. And then we have Benoit connecting remotely. He's also.
Hi, hello. I hope you hear me. Can you hear me?
We hear you just fine, Benoit. Salut.
Okay, perfect. Salut.
All right, so I'll just share my screen right now just to show you some pictures of CFHT. Do you see that?
Yes.
We can see it just fine.
Okay, all right. So this is our observatory, the Canada, France, Hawaii Telescope, as it looks up at the summit. We are a 3.6 meter facility. So basically the diameter of our primary mirror is 3.6 meters. And there is lots of science that we can do along with good weather and plenty of instruments. This is our office, our headquarters here in Waimea. And this is a picture of the control room where we are right now. So that's to just give you an idea of how the control room looks. And you can see there are lots of monitor screens over there, and I'll talk a bit about that pretty soon. This is just to give a sense of what kind of capabilities we have. We have imaging both in optical and infrared. We also have spectroscopy, so that is basically taking rainbows of whatever we are looking at in the sky. But this is in the optical as well as in the infrared. And then we have a special instrument, SITEL, which we have right now. Like for tonight, we have SITEL on sky, and SITEL is able to do both things, take images as well as spectra. So that's pretty cool. When I talk about images, we are looking at something like this. So this is an image from our optical imager, which is called MegaCam. MegaCam is able to do imaging in a lot of different filters, like a green filter or a red filter, and you're basically able to see light in different colors. So this image, right, what you see over here is of a big giant gas cloud, which we call a nebula. So there's active star formation that happens in this kind of nebula. And what you're able to do with MegaCam is image this kind of region in different filters to study the light at different energies. And this is a composite image. So all of that put together, combined in a very nice way. So that gives you such a beautiful picture. So that's what we get with MegaCam. With our spectrographs, we have spectropolarimeters. And with that, we get something like that looks like this. So this is a spectrum. This is a spectrum, and when you look at spectrum, you're basically looking at light at different energies. The lines that you see are dipping down. Those are basically absorption lines from the gas. So that's the different kind of data. And when we get to the second part of this session, when Benoit will talk about what we actually see with SITEL. So that's just to give you a glimpse of what kind of things we study. We look at all the different kinds of
Viraja, can I ask a quick question? Are you
yeah,
guys on
sure.
Sky right? You guys are on Sky right now, and Lisa's
We
sitting
are
down.
on Sky. Yes, we are on Sky right now.
And it looks more gorgeous than predicted, I think.
Well, there
Don't
are
see too many clouds.
Yeah, there are some clouds which are definitely making Lisa very uncomfortable, but yeah, but yes, we are observing right now.
And you're using SITEL right now?
Yes, we are using SITEL tonight. So with all the different instrument capabilities over here at CFHT, we can do different kinds of science, all the way from objects like stars or planets, exoplanets, all the way to galaxies, clusters of galaxies, even the gas which is in between galaxies, which is intergalactic medium, interstellar medium. So we study a lot of different things at CFHT. So with that, I'll shift gears a little bit and talk about what we actually do during an observing night. So as you see, we are right now in the control room. All of our observing happens remotely from the control room. It's not at the telescope, which is up at the summit. So all the observing happens from the control room. It's all a one-person job here at CFHT, and those spectacular people, we call them remote observers. They basically single-handedly do everything during a night in a continuous stretch of 12 hours. So they come in the evening, they get everything set up, and with that, there comes safety checks. So how's the weather looking like? Is the observatory okay? If there are not any, are there any things that are concerning inside the observatory? And I can show you a quick, so these are some of the cameras that are installed inside the observatory. So they look at different things, if there are any leaks, if there are any issues with the piping, and all of those things. So they check for observatory safety, weather check, and then they decide that, okay, it's safe to open up, and that is when they actually open up the dome. and
So Viraja,
start
really
observing.
quickly, so I think we have about 3 more minutes or so with you guys. So I was wondering if we could, yeah, it's really quick.
Okay,
I was wondering if we
well,
could pass to Benoit just to go over the instrument and like kind of what the purpose of the instrument is and what y'all are observing tonight.
sure. Thanks
sh-
for that. Thanks for that reminder. I'll switch over to Benoit. So Benoit, you
Okay.
can talk about
Yeah, thank
CL
you.
now.
Yeah, so let me share my screen quickly. Okay. So just to start with, just to show you, here is an image of what we are just observing right now. It's in fact, it's a calibration field, so there is nothing protected. I can show it. So what you see here, it's 2 images. It's related to the instrument that we use. So now I move to this picture here, which is a picture of CITEL, the instrument. CITEL is a Fourier transform spectrometer. And so basically, the goal of such an instrument is to, I mean, the techniques behind that is that we use a Michelson interferometer. So the light comes from the telescope here on the right, and there are 2 mirrors here. One is fixed, the other is moving. And when we move the mirrors, we sample not directly the spectrum, so the rainbow, I would say, but the Fourier transform. So it's a mathematical transformation of a spectrum. And so just to show you, so we have 2 cameras just to avoid losing light. And here I just show the path. So the reflection goes to one mirror to the other. And we have one output here and the other output here. And so in the end, we have these 2 cameras that corresponds to the 2 cameras that you see on the image. So with such an interferometer, the good thing is that, as I showed, you have an image. And in fact, when you scan, you sample in some way the spectral range. So the instrument provides, in the end, 1 spectrum per pixel in the image. So here I show you an image of what is currently observed. When you observe with a single color, what we call a monochromatic source, you end up with those rings that is related to the instrument. And when you change the steps, so move the mirrors, you see the rings that are moving and get more large. So if I just pass through the things, you see that those rings move. And this data from these sources is used as calibration. So now, since I have very few time, I show you other observation that we have done. So this is a galaxy that has been observed with CITEL. And you see here, when we go the observation, we see rings that goes to the field. This is related, in fact, to what we're observing. What we see here is just the emission from the skylines. You have maybe seen a satellite that just bothers us a bit. But you see here we have this kind of observation with these interferences that we go. And so the goal, so at CFHT, we provide data that is usable for science. So now we'll show you what it looks like when it's reduced. So when you have the data that is treated, you have, so maybe it's not the best solution to show you, but just to show you like that. So the image is here. So when I sum the whole spectrum, I get a very nice image. But when I look closer to the spectrum here, so the spectrum is the lines that we have below, we see that we have these kinds of emission lines. And if I just go on that, and that now I just have an issue just showing the right thing. Sorry about that. So here now, if I move towards the spectrum, we see that we have things that moves in the image. And in particular, we see those regions here that are H2 regions inside this galaxy. And these H2 regions just moved because of the rotation of the galaxy. So there is a Doppler effect, like when you have, a police car that comes towards you, you have a sound that the notes change when it passes the other direction. It's exactly the same here. It allows you to measure the velocity of the material. So it's very fun because you can really see it clearly. And when we look at the spectrum also, we see that there are other emission lines that enables you to get an idea of what's the metallicity, what are the physical conditions in that. And there is the last thing that I wanted to show you is that, in fact, this data, you can wonder, okay, there is a nice galaxy, but it's not in the middle of the field of view. And you're right, it's not in the middle, but it's done on purpose because the goal here is to study the material that is not inside the galaxy, but outside the galaxy. It's a galaxy infalling into the Virgo cluster. So I'm sorry about that. Just 1 second to change my buffer. And that's it. So then if I really work on the data itself, sorry, I show it this way, then when you move it, so now it's been just to make to be able to see the things I want to show. But here you see those kind of sorry, I have to put my cursor. You see those kind of filaments that you see here that are in fact tails of gas that is stripped from the galaxy due to its interaction with the intercluster medium. So this is really interesting because the kinematics of these filaments here provides us to the scientists the possibility to reconstruct the orbit of the galaxy when it's infalling into the cluster of galaxies. And this is really important to understand how galaxy forms, how they evolve, and how the star formation is quenched, and how we made elliptical galaxies from those nice spiral galaxy that we observe. So it's really the goal here of this data I have just showed you. And I think I'll stop here. Be free to ask any question, of course.
Okay, thank you so much, Benoit and Viraja and Lisa.
Yes, thank you. Getting a big round of applause here. Yes.
Thank you so much for having us.
Telescope, folks.
Thank you.
We have an observatory knocking on the door, so unfortunately we're gonna have to leave you. Bon chance, clear skies.
Aloha.
Merci.
Mahalo.
Aloha. Bye.
Okay, wait, another telescope knocking at the door. Wait, let me see who's down here. I don't know. Let's see. Who do we have here? Wow. Yes. Okay, so let me remove these spotlights. And let's see who we have. Whoa, we have lots of people here. I think, let's see, we have Percy Gomez and Christina Vides. Wait, is that Keck calling us?
I think that's Keck.
It's a Keck telescope. All right. Welcome, Christina. Welcome, Percy.
Hello, hello.
Aloha.
It's good to be here tonight. How is it going?
We are excited to have you both. We're excited to have you both. Okay, so you're now co-hosts, and let me spotlight you both. Thank you for joining us, and apologies for the timing. We appreciate your flexibility. What is going on with your science tonight? Are you actually in Waimea at Keck observing?
I am not. I'm actually in Irvine, and I'm controlling the instrument from Irvine. So I'm in Southern California. My advisor is in Northern California, and we're going back and forth controlling the instrument. And that's pretty amazing that we can be 6 hours by plane away, and we're still able to control these giant telescopes.
Christina, do you mind turning your mic gain up a little bit? It's a little bit hard to hear you here.
Sorry about that.
You try test again?
Let's see. Oh.
Or maybe just speak like really close to your microphone.
Yeah, how's this?
It's better.
That's better.
Yeah.
Okay, I just need to be up close to it. Perfect. All right. Yeah.
And so, Percy, where are you connecting from? Sorry, Christina, to cut you off, but Percy, where are you connecting from?
I'm connecting from home.
And where is home, Percy?
In Hawaii, but I'm not either at headquarters in Waimea or at the summit. I'm just at home, hanging out with my cat.
So pajama mode then tonight, it seems like.
That's right.
Yes.
So
what are y'all looking at tonight?
Yeah, so let me share my screen because I have a couple slides about what we're looking at tonight. So first I can take you through a couple of slides, and then we can actually go and check out what's going on on the telescope. So
okay.
Yeah, tonight we're looking at this beautiful protoplanetary disk called TW Hydra. It is the closest protoplanetary disk to us at about 200 light years from Earth. And that makes it a very favorable spot to search for protoplanets because it's so close to us. And typically regions where protoplanetary disks are found are gaseous, cold, and dusty, and they're pretty far away. But this one being so close lets us look very close at the star. And
Christina, I'm just gonna repeat. This is not my science. So I'm gonna try to repeat what you said. It's still a little bit hard to hear you. So it sounds like you're looking at a protoplanetary disk, so a disk of gas and dust surrounding a young star. And I guess the circles in that image that we see there are either planet tracks or diffraction spikes or some combination thereof.
So these are rings and gaps that could be caused by planets sweeping up material in them.
Okay, so these are rings actually in the gas and dust that the planets, the protoplanets, the forming planets have cleared, and they're now coalescing material onto themselves.
Yeah, exactly. So we're hoping to image really close up to the star so that we can either find more find a protoplanet or more rings and gaps. So I'll tell you a little bit how we're doing that. So we're using a method called non-redundant masking, which you'll see in a little while causes a snowflake-like pattern on our detector. What this does is it converts a telescope like Keck 2 into an interferometric array by placing a mask after the telescope and after the AO system in front of the detector. And you may have heard of interferometry being done with Keck 1 and Keck 2, but this method allows us to do interferometry with just Keck 2. So what we do is we calculate quantities that allow us to reconstruct an image. So we actually are doing exoplanet direct imaging. And if you've ever seen exoplanet direct imaging with a coronagraph, you know that it gets very noisy close to the star. And you typically see these large speckles near the star, but this method allows us to remove that noise so that we can search for large protoplanets on solar system-like scales. Generally, this is Saturn-like scales, but because TW Hydra is so close, we can get image down to about 2 to 4 AU. So that's about between Mars and Jupiter. Are you
okay? So, Christina, I will just try to repeat a little bit of what you said. So it used to be that Keck 1 and Keck 2 worked in tandem as an interferometer. So basically, the combined power of the two telescopes. This is a really famous example. One of the Nobel Prize recently was to look at the center portion of the galaxy and look at the stars moving around. And you need really good angular resolution to do that, more than you can do with a single 10-meter telescope. So why not combine the two of them together? So for this technique, there's a mask that actually goes on. So don't do that anymore. Actually, Keck 1 is on engineering tonight, so they're doing a bunch of tests on Keck 1. And Christina and her collaborators are just using Keck 2, so only 10 meters of glass. Sorry. So they're using a specialized mask to basically create an interferometric array with the Keck 2 telescope. And this special technique, I guess you lose light in this process, right? But you gain angular resolution. So you need to look at things that are very bright. So you basically, it's like left eye, right eye. And so it triangulates the two. And so when you close one eye, you kind of lose light, but you can triangulate better what you're seeing. So that's how humans do it. That's how it's just optics in the end. So this is how this methodology works on the Keck 2 telescope. And so their goal here is to look at very close by, bright, forming planets, and they need really high angular resolution to be able to pick that out. And so this is the technique that they're using.
Excellent, excellent, yes. And so I really hate that we have to run. Thank you so much for sharing. Percy, before we go, would you like to add anything to what Christina was sharing about the science you're working on this evening?
Matt's done a pretty good job explaining what, the scientist is looking for. And, at Keck, we're just trying to make everything, work. So scientists like her can do their best that they can.
So I just want to mention, thank you, Percy, and thank you, Christina. I just want to mention that you actually put up the live screen right now of Keck observing. So if you want to take a second to just explain that, and then I think we're maybe have to go after that.
Yeah, 1 second. Let me get to a little bit more exciting control. Yeah. Let's see. Are you able to hear me better now?
A little bit. I can repeat. I'm much more familiar with
Okay.
these screens.
Great. Let's see. So what we're doing right now is we're, let me switch over to another real. Okay, perfect. So here we actually have, are you able to see the detector?
Yep, we
Yeah,
can. Yep.
yes.
Yeah, okay, awesome. So we're actually, you should see the snowflake-like pattern. Since the background is a little bit high at L band, it's a little difficult to see, but we take images in the corner up here, and we take about 20 images, so 10 images in each corner. So this corner up here and this corner down here. And then we take the median of those images and subtract them, and then we can see our snowflake-like pattern much, much better. Let's see a little bit about what's going on. So we're also looking at the intensity of the adaptive optics wavefront sensor too. And we also have, here we have the detector status. So how long, we know how long we're exposing on the target. We know what mask in the filter, what wavelengths we're observing at, which is we're observing at L prime, which is where we are most sensitive to accreting protoplanets, very rapid accretion, because the gravitational potential energy converts to accretion luminosity as a planet forms. So we're really looking for planets that are rapidly forming.
Okay, thank you so much. So just to repeat really quickly, so this is one of 4 screens, right? So you're doing 4 BNCs, yeah, so normal. And so half the number of screens of Gemini, just saying. And this is the display right now. So you just took this image, right?
Mm-hmm.
And so this is the NERC2 image. This is using this specialized technique. And as Christina said, they're gonna move the telescope around to have the source, the star and protoplanetary disk, illuminate different parts of the detector, and they're going to use a mathematical technique similar to what Benoit just explained for Sitel, somewhat, and then they're going to basically pull out the protoplanetary disk from that image. And so even with 10 meters of glass, even with these super sensitive instruments, you have to get really, really creative. And you have to use this incredible amount of information all night long. It's 3 hours time difference, so it's already midnight in California, and so astronomers have to stay vigilant all night long to make sure that they're getting everything they possibly can. So wish you guys good luck, clear skies.
Thank you.
Thank you so much.
Thank you for joining us and sharing your science with us.
Bye, everyone.
Christina,
Thank you for having us.
Bye.
Telescope.
Bye, guys. So I guess is this the end of the evening, or do we have one more observatory? Are we?
Oh yes.
Break, or?
You know what? We have about 6 minutes, and we're saving a surprise for last. So do you remember earlier in the evening we asked you to submit some answers for a survey? What kind of object would you most like to see? Well, our next science guest, JD Armstrong, has an image for you for that answer. So we're going to be moving summits. We're moving from the summit of Maunakea to the summit of Haleakalā on Maui, which is where JD Armstrong is an astronomer for the Institute for Astronomy on Maui. Welcome, JD. Thank you for being so patient.
All right. Thank you. Yeah, it's good to see you. Can we go ahead and turn on sharing so I can share my screen and
Absolutely.
we will show. All right.
Yes. So welcome. Thank you. And
there we
yes,
go.
you should be able to share right now. What was the winning object? The Rosette Nebula.
The Rosette Nebula. Yes. Okay, so I programmed this in
Can you
just
talk a little bit
for
closer to your speaker, JD?
let me set the I've got a Bluetooth thing that should be doing this, but it's not. Okay, here we go. One sec. Okay. Is this a little better?
Yes, yes, thank you.
All right. Okay, so we I programmed this observation in special for everyone there, and we're going to. This was observed. It looks like on, I believe it was Haleakalā. Yes, OGG. That's Haleakalā. This is using the Las Cumbres Observatory network of telescopes. So it technically could have been observed at many sites, several different sites, but it was observed here. And so here is a quick preview, and let's go ahead and see what the color image turned out to look like. So it might take a moment, drum roll. Oh, there we go. Okay, it's a little bit, yeah, the colors are a little bit off, but here is the Rosette Nebula, or at least part of it, as observed, special for you tonight.
So just to be clear, JD, this was taken like an hour ago. Is that right? At the request of the audience?
Yes, at 5:35 Universal Time, so that would be 7:35 Hawaii time. So about an hour and a half ago.
So right after, that's why we put that survey at the very beginning, asking you so that I could let him know what the answer was that everyone most wanted to see. And then Anik and I sent him a message, told him what it was. He submitted the user request. It was observed, and now we're able to see the object right here. Isn't that amazing? Yes. Yes. Yes.
And
yes,
second place, I believe, was Messier 104, the sombrero.
The sombrero.
So everyone gets a bonus. And here we go.
Bonus.
Okay, come on.
Whoa.
They're building suspense by loading it slow. You notice that?
Oh, look at that gas dust in the arm spiral galaxy.
And we can zoom in a little bit. There's a little bit. Yeah. So you can see these lovely dust lanes here. Yeah, very, very nice. Very beautiful galaxy.
Wow, this is amazing. Let's give JD a round of applause for sharing these amazing images with us to close out our evening. JD, thank you so much for submitting these observer requests on the fly and allowing us to see these beautiful images to wrap up tonight's session. And let me just say, JD has been with us since before we started the session, so that he could get those answers from your survey and submit those observer requests. So he's been working on this the whole time we've been up here. So JD, thank you so much. We appreciate you and everyone who's still on the Zoom for joining us. I'm gonna go ahead and log out now, and we're gonna hand it back over to our MC, Emily, to finish this session. Thank you all so much. And you've been an amazing audience for this 1 year anniversary of Astronomy on Tap with Shadow the Scientist.
Astronomy on Tap mugs with our wonderful logo. And as
You guys.
And as it is a big anniversary, we want to give a big mahalo to Hilo Town Tavern. Hilo Town Tavern. Months for us with all of our names. We have Nick here, Joy. All of our team members are here tonight, unfortunately. Jasmine, Emily, that's yours. That's mine. Let's see, we have Emma, Leilani, and Jenny. So thank you so much for your contact. Can you take us back to our slides? Oh, yes, and as a reminder, we still have our question here of do wormholes exist? Participate in our poll, and it contributes to our future prizes for Astronomy on Tap. And speaking of future Astronomy on Tap, our next Astronomy on Tap is going to be May 1st at 7 p.m. May Day, also, and here in Hawaii, May Day is Lay Day. We are going to be celebrating Hopeful Lay, the Lay of Stars. And we'll do a special hint. We're also going to be looking at doing some lay making during our next Astronomy on Tap at 7 p.m. on May 1st. I'll also plug May 1st, Astronomy on Tap. May 3rd, Astro Day. Yeah. All right. Aloha to all of our team, our speakers, everybody who made Astronomy on Tap possible. Let's give a big thank you to Hilo Town in order to be checking out the latest things that are happening with Shadow the Scientist. Once our donation box. Our observatory experience. You get on the wait list. You have to go on. That's cool to send me emails about when you next time sign up. We'd love to hear your feedback about Astronomy on Top sessions. If there's anything interesting that you guys want to learn more about, or sessions that you would like to see or have something like that, please let us know. And we'll close off with thank yous to everybody, but I want to make sure that we get a thank you for you guys who have been here. Many of you have been coming. Yeah. See you again very soon. Mahalo. Okay, so there you go. Thank you. You can log out of the Zoom. Yeah, I think once we log out of the Zoom. Oh my god, it was amazing. Good job. We finished at 9 on the dot too. Yes.